Okay, so welcome everyone. Very good evening. I hope everybody's doing well. So what we're going to do is continue with reinforcement learning or online learning that we were talking about last time. So let me share my screen and recap where we were. So okay, so I'm just displaying the syllabus page just to kind of recap where we are in the larger context of this course. So last week we talked about bandits a little bit. Okay, so last week it was we were switching topics, so we were finishing up the transformer architecture, and then we started talking about bandits as a way to think about sequential decision making. Okay, and so that set of modules are 9, 10, and 11. Okay, so we started with A/B testing. What's one of the I guess issues with A/B testing in terms of sample efficiency, and then we looked at what is the problem. The problem is called multi-armed bandit, where you take previous outcomes into account while deciding whether to show the next person version A or version B. Or basically, when you take a decision at time t, you take into account what all happened in the previous time t minus 1 periods. Okay. Whereas in A/B testing, you don't do that. So that's the, I guess, the improvement or the change. We'll continue talking about it today. Last time we saw a couple of algorithms. Epsilon-Greedy is one of the algorithms. Then we also saw UCB or upper confidence bound algorithm. These are all solutions to the same problem. The problem is how to make decisions based on what has happened before. Okay, so therefore, I mean, how to make decisions is basically, you can think of that as a function, right? A function, a given input, which is what has happened before in some form. For example, like a vector or something. It needs to output a decision, and decision is basically a generalization of classes. So if you have 4 decisions, you just think of having a 4-class classifier type of outcome space. So you just need to figure out which one of the 4 decisions you want to take. Okay, so you need to think of decisions like this, which depend on history, what happened in the past. So continuing on, what we'll do today is talk about contextual bandits, and hopefully start really scratch the surface of a little bit more general framework, or little bit more general problem, and a solution of it. Okay, that solution is going to be called Q learning. We're going to only look at one solution for the full reinforcement learning problem. Whereas for the multi-armed bandits, we have, as we said, as just mentioned, we have already seen a couple of solutions, Epsilon-Greedy and UCB. And we also talked about Thompson sampling, which is where I'll resume today. So those are that's what we are doing now. And just to give some more context, why we are doing that now is that this is relevant to assignment 4. So if you look at assignment 4 questions, there are basically 3 questions, 2 of which are related to bandits. Okay, so question 1 is not related to writing any programs. So this is something that you can, you use Markdown, or just, use, if you're using an IPython notebook, you can just use Markdown syntax to answer these questions in the cells themselves. Okay. And question 2 is the one which is related to the algorithms that we have seen last time, and also what we'll see today. So so Epsilon-Greedy is the algorithm that we saw last time. UCB1 is also the algorithm that we saw last time. And Thompson sampling is something that I started last time. But I'm going to talk about this aspect, conjugacy, today. Okay. Now here, this question says, hey, write down individual functions for, or write down code for for making these decisions. Okay, these algorithms or solutions are basically, as I said, you need to think of them as functions which take input, which is history, and produce a decision, which is just going to be one of the 3 actions or 4 actions. So in this question, it's 5 actions. Okay, but you'll see that these functions are not complicated. There are literally 1 to 5 lines of writing in a short script. But it's good to understand what the core problem is with respect to decision making, and how it differs from all the prediction problems that we have seen so far. use and finally, so that's what. So what I'm going to say is that question 1 and 2 are going to be covered by today, so you can get started with assignment 4. But question 3, we will not get to DQN potentially today. We will talk about DQN next week. That gives you about a week to finish, before the deadline of this assignment. Okay, so you have roughly 1 week to work on 3. I mean, you can certainly work on 3 even based on today's lecture. We are going to cover reinforcement learning, but we're not going to look at specific semantics of Q, specific semantics algorithm that has been considered here. Again, in here, we are not writing any extra code. We are actually going to use a starting point as one of these repositories and do some sensitivity analysis, which you did in assignment 1. So this assignment is not very complex. So certainly ask me or Teng during the coming weeks, or stay back during office hours if you already started this assignment. So that's what I wanted to quickly talk about in terms of logistics. So to recap, last week looked at bandits, and this week and next week we're gonna look at reinforcement learning, and these, till next week is gonna be the material for assignment 4, and assignment 4 is due on, I think, let's see, it's due on 20th. Okay, and yeah, and then so that's about the lecture content and the assignment 4. I also want to quickly remind before I get into the content that the project is due on 27th, as is listed here. So artifacts of your project, like the report and code and sample data and things like that, they are due on 27th, and 28th you will have a chance to talk about it and present it to your fellow classmates, and that's going to happen on 28th. And the time slots for the presentations, I think we already discussed last time. They're already there in the Google Sheet link from last time, and I'll share it. I mean, it's probably not relevant now. I'll share it right, a week before, as well as on the week of the presentations. Yeah. Now let me come back to some details. I just want to use this opportunity to again talk about the goals. So we were on module 9. So what we did last time is try to answer the question of what is online learning, or what is online learning or sequential decision making. Okay, online or sequential is the key word here, and how it's different from supervised learning. So it focuses on decisions, and it's also doesn't follow a batch type of a process where you have an X, Y pair, type of data, like most of the data that we have talked about in the previous sessions. It's not like that, although you can use supervised learning, and I'm going to talk about it a couple of, when the context arises today. And I guess in general, you should know the difference between forecasting and decision making. So for example, there's a big difference between going from, let's say, test accuracy of 80% to 90%, or sorry, 80% to 90%, and making decisions which improve your revenue by 80 to 90%. Okay. Many times what happens is you may be able to improve forecasting accuracy, whether it's recommendation systems or forecasts of prices, or things like that. Whatever it is, you may be able to improve them by, of course, by your usual supervised learning techniques. But that improvement in model prediction may not translate into improvement in decision making. Okay, improvement in decisions that you can take. Okay, for example, the decisions that you can take is, for example, in the finance domain, let's say in the trading domain, you would buy or sell stocks. Okay. But buying and selling stock are in the decision space. You predicting prices or returns or whatever it is not exactly the same as making decisions, right? You can also, of course, map them and maybe relate those to numbers, but that's a big takeaway, that just focusing on prediction problems is not enough. It has to be tied to downstream consumers, or downstream tasks which consume this predictions to do something valuable for the firm. Okay. And last time we looked at multi-unbounded problem, we defined it and saw a few solutions. Today I'm going to continue talking about Thompson sampling and the conjugacy idea. and we'll briefly cover contextual bandits and then move over to reinforcement learning. In RL, certainly by the end of today, by the end of this session, you wanna be able to say what is reinforcement learning. We'll also introduce a mathematical framework or a language to talk about different elements of a solution strategy, okay, of a way to approach the reinforcement learning, a way to approach and solve the reinforcement learning problem. Okay? And that's through this mathematical concept called Markov decision processes. Okay, it's a it's a simple enough or straightforward enough idea. It nicely captures the captures at least the vanilla or the basic version of this problem. Okay, and there's going to be other objects or other concepts that are introduced. The first one being policies. Policies, is just functions. Okay, they just map something to a decision. And we'll also look at what are called value functions. This is going to be made clear when we get there. And these are going to be essential ingredients to define a solution for the reinforcement learning problem. Okay. So that's my very quick overview of what the goals are, as well as the logistics. And if there are any questions, it's a good time to ask before I jump into the material. You can also use the chat. Although I've split module number 10 and 11 as two separate modules, depending on where we are, we may be able to cover some more for example, module 11. Okay, it's the same slide deck. It's just I've split it into two modules just because if we run out of time, we'll cover some later part of the slide deck in the next session. Okay. Okay, and before I get into, I'm going to switch over to annotation in a second. I want to give you a few references that are useful, maybe not right now, but maybe after the session, you can go back and check. First reference is this is a page on one of Git repositories. It's a wiki, basically. And so it has a nice set of content organized, which it's useful to explore. It has some bunch of links to videos, courses, as well as books, as well as how to debug code when you write code which is related to techniques which is related to solutions which solve the reinforcement learning problem. Okay, it's not a single problem. I mean, the reinforcement learning problem, just like supervised learning problem, has many variants depending on which application you're working with. So it's a nice set of links, including one of the links, which is this book that is also linked in our syllabus page as one of the references. Yeah, and it also has a bunch of both repositories that you can use, like implementations by different researchers that you can try out. We'll actually see one of the implementation in the assignment. So this link here corresponds to actually let me click open. Yeah, it corresponds to a bunch of solutions for solving the reinforcement learning problem written in PyTorch, because as you'll see, the underlying solution strategy involves the same ideas that you've applied in assignment 2 and 3 or all the previous sessions, which is basically backprop and underlying neural network and so on. So there's some connection to neural network, but you'll not see it today. And we'll see it when you look at assignment 4's third question. Okay, the third question involves a small neural network and training it. And so that's this code base. So you basically will poke around this code base in that question. And so that's the first resource. I just shared it on the chat. Second resource is an interview with a practitioner. This is something, it's not super critical that you read it, but it's basically somebody who tried to apply reinforcement learning at different firms. So you can, this is actually a podcast, but you can look at different applications and get a feel for, what's the connection and this, it's just a practitioner's view. So you can look at it. Yeah, and just to give you some examples of very, I guess, not so obvious places where reinforcement learning is trying to be, people are trying to use it, is for for even designing compiler optimization. So this is something that most of you will probably not see unless you are in computer science or some, even in computer science in a very small sub area. So even there, folks are trying to use ideas from reinforcement learning. And this is something by Facebook Research. So you can have a look at it. But I don't, there's just an example to tell you that, there are a lot of different applications to RL, but we'll look at basics in this today and tomorrow, today and the next session. Hopefully that will give you a good idea, and then you'll see where all you can apply it in applications. So with that, let me before annotating, let me come back to, sorry, I'm going through a lot of slides here. Let me come back to where we were last time. So last time we talked about A/B testing, and we said, oh, let's say there are two decisions, A and B. Those are the two, let's say, websites or so, and so on. Then to figure out whether A is better than B, you want to do a randomized control trial. That's what A/B testing is. And what you do is every time a user comes or some unit comes, they're exposed to solution A or exposed to solution B. Okay, or they're exposed to decision A or decision B. Okay, you take a decision when somebody comes, right? So in A/B testing, what you do is, because you want to make a decision A or B, to figure out which one is better, what you do is in this testing phase, you're going to flip a coin with equal bias and make a decision A when if the coin lands heads, and flip, and if the coin lands tails, you make the decision B. Okay, and you do it for a predetermined amount of time based on your estimate of how much you think a priori A is better than B or B is better than A. Okay, so that predetermined amount of time, or what you call formally a sample size, so that's something that you choose beforehand, and you have to commit to that, in the sense that if it turns out that you think that A is better than B by 5%, relative percent, then there are some online calculators that you can use, which will tell you, hey, if you think that A is better than B by 5%, then if you really want to, collect data and then, use a hypothesis test to actually show that it is actually the case, then there'll be some sample size number that's going to be recommended, like for example, 10,000, which means that you have to run this test where A is exposed, decision A is taken for 10,000 users, and B is taken for the decision taken for another 10,000 users. So you need to do this. You need to basically test on 20,000 folks, because there are two decisions, 10,000 per decision. So you need to expose this testing to 20,000 folks, and after those interactions, you will figure out whether A is really better than B through a hypothesis test. Okay, so that's what typically goes on with A/B testing. But last time we reasoned that if it turns out, even after, let's say, 100 interactions with users, solution A is already way better than B. If you can already see that by just looking at the average metric, for example, maybe clicks or sales or whatever it is, then why do you have to expose a lot of people to decision B from that point onwards? You should not, right? So you are inefficient. If you're going to spend another 9,000 folks, you're just going to expose it to B when you know that A is performing better by by only the first 100 interactions of users. Okay, so to deal with that, the idea of sequential decision making, or multi-armed bandits. Multi-armed bandits is just an example of that problem, is to rely on what has happened in the previous 100 interactions to take the 101st decision, previous 101 interactions to take the 102nd decision, and so on. Okay, so that's the sequential decision making, where you incorporate feedback, keep incorporating feedback, and improve yourself. Okay, but this poses a challenge because you're collecting data based on your decisions, and so the data is not is going to be, for example, biased in certain ways. For example, if you keep showing decision A, trying out decision A, you don't have much information about how decision B fare. For example, its variance of how good decision B is maybe high. Okay, so there is this idea, therefore, of trying to explore and exploit. And we saw that when we looked at the first algorithm for multi-ion bandits, okay, which is Epsilon-Greedy algorithm. So let me directly get there. Yeah. So what I'm now going to describe in the next 5-ish minutes is the 3 algorithms that we saw last time. Okay, third algorithm is where we'll again, resume back, and that's the formal start of this session. The first algorithm is, remember what we are trying to do is to figure out, there are k decisions in general, or 2 decisions if you want, or 3 decisions. And each distribution, each decision has behind it a distribution from which you can get a reward. Okay, so for example, if you take decision A, maybe 30% chance that this person buys your product. If you take decision B, maybe there's 20% chance that this person buys your product. Okay, so those 20% chance, 30% chance are basically random events, right? But you don't know a priori what is the chance. Okay, that's why you're trying to test, or that's why you're trying to learn which decision is better, and hopefully zoom in towards that decision most of the time. Okay. And so since there are chance events, each time you take a decision, there's going to be a mean reward or a mean performance, right, of trying out each decision. That's represented by mu k. Okay, it's just a Greek symbol to represent that. And our objective here is to depend on history. So we will look back, as in at any given point of time. So we're going to have timed interactions. So interaction number 1, interaction number 2, interaction number t. So at any given point of time, we want to say, hey, what all happened with what all decisions did I take, and what all happened with respect to I took this, I took decision A, the person bought something. If I took decision B, a person did not buy something. I log all that information. Based on information, I need to take a decision now at time t. And once I take the decision, again, something is going to happen. The person is going to, depending on the decision, the person is going to buy something or not. Okay. Um, and what I want to do is minimize cumulative regret or maximize expected rewards. Okay, so it's the same idea. So what is regret? It's just that if I knew A was always better than all these other options, I would always show that. Okay, and it has a mean sales rate or mean conversion rate of, or mean probability of, uh, uh, the probability that person, the users buy, if I show decision A, let's say it's 30%. That means that mu star is, let's say 0.3. Okay. So, and let's say little n is the number of interactions that um, you will have over a period. So for example, 10,000 interactions. So if I knew a priori that A was better, I will always show A. And the mean reward, the cumulative reward I would get by showing A is n times mu star, right? So 30% times 10,000. Whereas every round, I'm doing something, taking different decisions. Sometimes A, sometimes B. Hopefully, I take A all the time. That's what the whole point of trying to solve this problem. But sometimes I'll take B. Sometimes I'll take other decisions if they are there. Okay. And my objective is to minimize this expected cumulative regret. Okay. So if you take an expectation of this Rn quantity, which is the difference between what you would have done in hindsight versus what you have done over this period of n interactions, little n interactions, then that difference, you want to keep it as small as possible. As if, the best thing you could do is try A, but you can only get lucky you can only do that by getting lucky, right? If you don't know what are the mean rewards of each of the decisions and you want to try A, you just have to guess at A and take it, and only then the cumulative reward will be low. But that's but with a good chance you'll not do that, right? But the algorithms that we'll see, there are three approaches, or actually 4 approaches today. But last time we saw 3 approaches. They all try to do something so that they're able to make better decisions at time t based on historical data. Okay? And the first algorithm is Epsilon-Greedy, which is saying at any given point of t, you have taken each of the decisions, let's say A and B. You already, let's say you've taken decision A 30 times, decision B 70 times, that's fine. Now what you need to do is, out of the 30 times, how many times did you get a sale for edition A? And for edition B, you took it 70 times. How many times did you get a sale? Okay, so you just want to get an empirical statistic of what is the probability of getting a sale if you take decision A, what's the probability of getting a sale when you take decision B. That you can always compute. Now, given these 2 numbers, what you do is, with probability 1 minus epsilon, so epsilon is a parameter for this algorithm. Let's say 1 minus epsilon is a fixed number, right? With 90% probability. So if you flip a coin with some bias, let's say epsilon is 10%. So with 90% probability, you just pick B. okay, or A, whichever has the highest performance in the history. Okay, so you are depending on history. You're just saying, hey, with 90% probability, just pick whatever was doing well before. But with some small, some other probability, which is let's say epsilon by k, okay, where k is the number of decisions that you can take, you pick a random decision. Okay, and you need this extra randomness is precisely because your data is being collected based on your decisions in the past. So if you always took A, you never know what would have happened with B. So you need to moderate that, and that's the whole idea of exploration versus exploitation. And so the algorithm does that. Okay, but it turns out that this algorithm does fine. You will be able to do decently well with respect to expected cumulative regret. Okay, and you can plot curves like this. Here it's just a curve of how many times do you pick the right arm. So right arm as in right decision. So the last decision in this example has this example has 5 decisions, and the last arm has the highest reward. So here we are just showing for different values of epsilon how with what probability do you select the best arm, okay, which just happens to be this last guy. Okay, and so it turns out that for any value of, for many of the values here, you will be able to get to the right, you'll be able to pick the best arm, up to a certain limit. I mean, the limit is basically because you have epsilon 10%. With 10%, you will never pick that arm. With 10%, you'll pick a random arm. So of course, you're limited by that, and that's why these are not always going to 1. Okay, probability 1. That's this first algorithm. I hope it's intuitive. Um, any questions here? In case you're saying something and I don't hear, let me know, but I don't think I heard anybody. Okay. So let me next talk about the second algorithm. Again, the idea is to use history, somehow compress, when I say history, I just mean, hey, you tried action A or arm A or decision A 30 times and decision B 70 times. That's history. Okay, you tried them and something happened, right? So every time you try an action, you get a reward, or you get to see what happened because you tried that action or that decision. Okay, that's what I mean by history. So the second algorithm is not a algorithm which depends on flipping coins, because Epsilon-Greedy required you to, that epsilon was determining the bias of a coin flip, right, to explore or exploit. Here, the second algorithm doesn't require doing that. What it does is, again, the same idea. So this so it's gonna pick arms or pick actions based on a calculated number. Okay, so the number is B. Okay, the number is B. 1 number per decision. So let's say we have 2 decisions, then there are going to be 2 numbers. There are 5 decisions, there are going to be 5 numbers. So how do we get this number B? Okay, there's 1 number indexed by k, little k, and which is the number of decisions that you have, which indexes the number of decisions you have. So what is this number B? The number B is composed of 2 parts. Okay, the first part is just the same as what we were doing in Epsilon-Greedy. So in the sense that if you take action A 30 times, hey, out of those 30 times, what is the empirical average, or an average of your metric that you're tracking, okay, reward that you're tracking. So for example, you showed decision A, or you took decision A 30 times, and maybe you had sales 15 times, then the performance of action A or decision A is 15 by 30, right? Like something like 50%. 50% of the time you make a sale. Okay, so this is just the empirical average, mu hats. Okay, but what you also do is you can compute mu hat for every of your actions up to any given point, and then for each action you also add an extra term. And that term just depends on, hey, how long have you been interacting with folks overall? Okay, so the little t is, hey, you started time 1, now at time little t, which could be 500, so that little t is just that index. Okay, so numerator is just 2 log t. It just grows as a function of the interaction. Okay? So if you have interacted 500 times, the numerator is 2 log 500. You have interacted with your users up to 1000th time, then little t is 1000. Okay, so it's just a function of t. But the denominator is interesting. The denominator is actually saying how many times have you played this arm? or this action or this decision. If you have taken this decision a lot of times, for example, um, if you have always taken this decision, for example, the denominator is going to be just t itself. So this numerator by denominator, log t by t, you know that log t is a small number, whereas t is, a small number relative to t. So this number, this extra term is going to be very close to 0. Okay. Whereas if you did not take this action or this decision too many times, then the denominator is going to be small, which means that this second term is going to keep growing. Okay. And the intuition is that the second term is the one which is trying to make you explore. Okay, so very similar to Epsilon-Greedy. Remember, Epsilon-Greedy, if you did not have the second term, you would always be taking decision based on what happened in the past. Okay, whatever did really well, whichever of the actions, whichever of the decisions did really well, that's the only decision you will be always taking. Okay, that's just greedy. Okay, that's called a greedy algorithm or greedy strategy. But instead of being greedy, you are tempering yourself by saying, hey, if I did not take one of the yeah, if I did not take let's say action K or decision K, if I did not take it uh, enough number of times in the past, okay, in the past, given that I've done little t number of rounds, then the second term is gonna, as I said, is gonna be large, and it's gonna grow large because it's growing as a function of little t, right? So it's going to grow up, and then it turns out that even if the mu hat is small, let's say action B, the mu hat was small, that you did not get any sales, but it turns out you never tried it, then the second term is going to be large, and therefore the B term is going to be large, and therefore since you're picking at any given time, you're going to pick the arm with the highest B value, this B value, you're going to pick that arm B. Uh, so that's the intuition between, that's the intuition for how this UCB algorithm is also capturing the notion of exploration exploitation. Okay, and why is it called upper confidence bound is because this extra term here is like a so mu hat is the mean, the empirical average. So you can have plus minus some extra term, like plus minus sigma, right? That's how you get a mean plus or minus some sigma standard deviation if you're thinking of a normal distribution. Here, forget about the minus sigma because we don't care about low values. We're trying to maximize rewards, right? Or minimize regret. So let's focus on the plus. So this extra term looks like a standard deviation. It's like something similar to a standard deviation measure. So that's why so mu hat plus this extra term is like an upper confidence bound of how well that arm is performing. Okay, and so if the upper confidence bound is high for some arm, then that's probably the arm that you should play now. Any questions at this point? Okay, so let me then go to the Thompson sampling algorithm, which is where we started last time towards the end. And this algorithm, again, it's the same problem. The problem is maximize cumulative rewards. Okay, a priori, you don't know which of the decisions is the best one, which of the actions is the best one. And over a period of time, you kind of need to zoom in onto the one which is the best one. Okay, you can always, maybe if you want to, if these algorithms don't seem intuitive, you go back and figure out how you would design an algorithm which would do well. Okay, it turns out you will probably fit into any of these patterns. You will eventually land up in any of these these intuitive ideas that I'm talking about today. Okay, so the third algorithm is called Thompson sampling. It's actually was developed, almost 80 years ago, 90 years ago. So this algorithm, by the way, is very robust. So you will see that in when you do assignment for question 2. Here, what you need to do is, at the beginning of time, you say, hey, I don't know which of the arms is good, which of the actions is good. Let's assume that the actions, the rewards for the actions are, the mean rewards for the actions are between 0 and 1. Okay, so let's say mu I is between 0 and 1. Okay, why is there a mean reward? Because as I said, for every action, there's a distribution corresponding to it, from which we can sample a reward. That's our mental model. So what we'll do, since there's since we don't know these mean rewards, we're going to maintain a prior. Okay, we're going to maintain a distribution over these mean rewards. Okay, and so therefore these mean rewards are actually now not parameters; they're now random variables. Okay, so we're going to maintain a distribution on them, and we're going to keep updating this distribution as we get feedback. Okay, as we move forward interaction to interaction, every interaction we get some feedback, right? Somebody purchased something, or we get a reward or not, basically. And from that, we're going to go from a prior to a posterior to a posterior to a posterior of these distributions that we're maintaining for each of the arms. Okay, and these distributions are distributions over the mu parameters. Are distribution mu random variables. Okay, so what you do is start with the prior, and then you compute a posterior at any given point of time, little t, for all of these arms I. Okay, so you compute a posterior distribution for this random variable mu I at round t. Okay, and how do you do that? How do you go from a prior to a posterior? You need to have a likelihood model, right? So you need to have basically you apply Bayes rule. So you have a prior, you have a likelihood function, and you can go to you can get a posterior. Okay. Um, and once you have the posterior distribution, so let's say any given point of time you have distributions over these random variables mu I. Okay, let's say you have steps 1 and 2. At any given point of time, you have these beliefs or distributions over the arms mean rewards. Next, what you can do to make a decision is the following idea. Step 1, the third bullet point is saying get a sample from each of these posteriors. So there are pi it, little I corresponds to the arm index or the decision, right? So let's say if there are only two decisions, there's going to be two pi's, pi a comma t and pi b comma t. Let's say a and b are the two decisions. Then you sample two numbers. Okay, so theta a and theta b, theta at and theta bt, or theta it in general. Okay, sample two numbers, one from each of these posterior distributions, and then your decision is just going to be whichever number is the highest, play that arm or take that decision. Okay, so that's the entirety of the algorithm. So in terms of coding it, it's very straightforward, if as long as you know how to go from a prior to a posterior. Okay, and we'll talk about that right now. And the idea is that the idea is that these posterior distributions capture your uncertainty over what the mean reward for each decision should be. So for example, if the mean reward for action A is uh, 0.9, like let's say it's 90%, and mean reward for action B is 30%, these beliefs should start concentrating on the value 0.9 and concentrating on the value 0.3 in the interval 0, 1. Okay. And if that is the case, then you can see that if you sample from each of these two posterior distributions, the distribution surrounding 0.9, the sample from there will be generally higher, and so you will be exploiting. But if there's a lot of uncertainty, you will sometimes be also exploring. Okay, so with that, let me actually switch over to the annotation. Any questions here? Either there are no questions or folks are not completely following. So, but it's fine. Please ask questions if you're not following what some details. So let me actually talk about this posterior and prior ideas with a diagram. So so as I said, let's talk about as a function of time. Okay, so what I'm trying to draw is t is equal to 1, t is equal to 2, t is equal to 3, and so on. So I'm just trying to show a temporal diagram. So at the beginning of time, let's say option A and option B have uniform distributions. Okay, so this is option A, that's option B, or two decisions. Okay. And since I don't know what these, which one is the better, so I'll have a distribution. These are priors, or these are just distributions over the mean reward. Okay, so I don't know what the reward is, so it could be anywhere between 0, 1 for either one of them. Okay, so at time t is equal to 1, what I'll do is sample a number. So maybe with A I get some number, with B I get some other number. Okay, So, and let's also assume that A's true mean is 90% and B's true mean is um, uh, A, A is better performing than B, and and B's true mean is, let's say, closer to 0, let's say 30%. Okay. Then you sample two numbers, the red dots there. You get sorry, no, the X is there, and you see that, hey, this is theta A comma 1 is greater than theta B comma 1. So what is comma 1 is just the t here. Okay, t is the 1, t is equal to 1, and A and these thetas are just these x's. Okay, some scalar values, some two numbers. Because this is the case, you say, hey, play action A. Now you say you play action A. Now if you play action A or take decision A, you get some reward, right? So let's say reward is that somebody actually got, did buy, a product. Okay, let's say action A is website A, where you're trying to maximize, selling a product, where your objective is to sell, sell the product, as many products as possible over a horizon. And so let's say somebody actually bought. Okay, so you showed website A, and it was such a nice user flow that people actually bought your product. Okay, and the messaging was so nice and all that. And so this is your data. So given this data, you're going to update your distribution over the mean reward to a slightly different distribution. Okay, so that's going to be maybe a posterior distribution. That's exactly called a posterior distribution. Okay, and B, since there was no information, it's going to be like this. Okay. Now, if you draw a sample, again, remember, I mean, it could, if I draw a sample from A and B, maybe it turns out that A happens to be smaller than B. Okay, in which case you'll play B, and you'll also get a reward, let's say 0. Okay, in that case, in the next round, you'll have the same distribution for A, because A is posterior, there's nothing to update. For B, because I got a reward 0, I'll have a distribution which is like this. Okay, I mean, getting closer to 0 because I had a positive reward. This is getting closer to 1. Okay, so now these you can already see that these actually, from these two distributions, you can see that I will be exploiting, because if I draw samples from A, the numbers will be closer here. And if I draw samples from B, the numbers will be closer to a lower value. So if I compare those two numbers, I'll probably be trying A more. And I'll also be exploring, because there's still a non-trivial probability that I may sample from this side, and I'll also sample from this side. And if that happens, I'll try B. Okay, and and eventually what you want is a distribution which is concentrated on let's say there were true values, okay, true fixed values for performance of A and performance of B, which is these exact same things. Okay, this is the same as this, but so what you want is through Thompson sampling, you want to have posterior distributions which kind of get closer and closer to the true performance. Okay, centered around the true performance of each of the decisions. Okay, but although this is not the goal by itself, the goal is to minimize cumulative regret. Okay, so that's what the algorithm is doing by estimating A and B's performance better and better, and doing exploitation. So is that diagram clear? Or any questions here?
I have a question. Why the reward in the second time slot is 0? I didn't understand this part.
Oh, I mean, I'm just saying it could be 0, it could be 1. Okay, so see if B's performance is, let's say, B's performance is, let's say, 20%. Okay, then reward 0 happens with 80% probability, and reward 1 happens with 20% probability. So with 20%, it could have gotten a reward 1, and your distribution could have been the opposite. Yeah. So I just wanted to show you one, I guess, trajectory or one sample path here of what can happen. Yeah. So it doesn't have to be 0 or 1. I mean, this reward 1 is only because, I said the true latent true probability for A reward 1 happens with, let's say, 80% or 90% probability, and reward 0 happens with 10% probability, let's say. That's the only reason why I chose reward 1, 0 here, but it doesn't have to be. Could be anything else. But this is all, eventually, if it turns out A is really better than B, in the sense that A really has this characteristic and B really has this characteristic, this algorithm will start playing A more and more because of looking at historical data and therefore maintaining the right beliefs and therefore updating the beliefs and all that. That's the sequential decision making pattern happening here, or the idea happening.
So at time T, the sample we got from the B decision is higher than decision A, right?
At sample, so
at time 2.
At time 2, yeah, at time 2, yes, exactly. Yeah, at time 2, I just, maybe it was not very clear here. Yeah, I wanted to have this one a little bit closer to 1. Yes, yeah. At time 2, it was like this. That's why I picked B. Yeah.
Yeah. Okay.
Right.
Thank you.
Yeah. Great question. Yeah. So, I mean, the idea is very simple. Okay. So I think the biggest challenge here is to get the conceptual framing correctly, like intuitively what do you want. You, as I said, I've been repeating this, I guess, for the 10th time already. You just need to use somehow historical data to take the next decision. Okay, and that's what we were doing in Epsilon-Greedy as well as UCB. And some, there's some extra ideas there, but that's the core idea. Somehow use historical data to make the next decision. Here, the historical data is all captured in basically these posterior distributions over the posterior distributions that you're maintaining for each of the decision or each of the arm, each of the action. This posterior distribution should capture everything that you know about this arm up to this point. Okay? So clearly, if I whatever number of times I played A, if I give, depending on the rewards, I should be able to zero in that, yeah, this A, decision A should give me 90% of the time a positive reward, let's say a sale, for example, right? And once you have such a summary, you know how to make decisions, right? So if you want to just exploit at this point, you can always play A, because this distribution's mean is greater than this distribution's mean. But you want to also hedge against the fact that maybe this distribution is not concentrated enough. Then you want to explore. Okay, and that is naturally captured because if these distributions are too concentrated, that means that you've already explored B quite a bit. So there's no need for exploring B anymore. You can continue to take A because A's mean reward is high. Okay, so that's conceptual idea. And the same ideas, you can actually draw similar plots for similar, I guess, temporal diagrams for both UCB and Epsilon-Greedy, but I will not do that right now. If you want, we can do that maybe in the office hours, right after the office hours. Okay, but let me move forward. So what I want to talk about now is conjugate priors. How do you go from a prior to a posterior, right? And we know this, apply Bayes rule, and we've done Bayes rule, for example, when we're talking about naive Bayes classifier and so on. So here, but in general, it's hard to go from it's hard to do this Bayes update, okay, Bayes update, going from a distribution to a distribution. If the distribution is a parametric distribution, still it's unclear how to go from a prior distribution to a posterior distribution. So what do I mean by that? Let's say you have so I just want to quickly illustrate something. So let's say you have a continuous random variable x, okay, which means that you have a prior distribution, right? So let's say x has a prior distribution. Let's call it prior, which is little x, x is equal to x. And you have a posterior distribution. So you want to compute the posterior distribution again. Posterior distribution on x given, let's say, some data. Okay, let's call data y. Actually, I don't want to call y because they're confused. Let me just call it data. Okay, so this is a posterior distribution. Posterior distribution is nothing but given some extra information, give me an updated distribution over x. Okay, so I'm just writing the Bayes rule now. So this is just probability of data given x times probability of x divided by probability of data. Okay, so instead of data and x, you can just substitute a and b, and you will see that this is Bayes rule, right? Now, this computation is messy because let's say p of x, if it's, let's say, it's Gaussian distribution, and probability of data given x is some other complicated distribution, then sure, numerator you can just multiply two distributions. So when I say you want to compute a posterior distribution, you actually need to find p of x is equal to little x given whatever data. Data is not a random variable anymore here. It's given some value for every x, right? So maybe if x is a real number, then you need to completely describe the distribution, right? So that means too many values here. But anyway, so numerator is fine. In the denominator, you actually have to do an integration, right? So integration of the probability of data comma x. Let's call it dx. Sorry, I'm writing in a little bit um, of informal notation, but basically you need to marginalize out x. Okay? So this, yeah. So this is not easy to do. Okay, and numerator also, if you multiply two things together, um, uh, it's fine. You can get a mathematical expression potentially, but you need to ensure that this is actually a distribution, right? So the denominator is important. So for every x value, you need to find the denominator. Sorry, not for every x value. For you just need to find somehow this normalizing coefficient or normalizing number correctly. Okay, and in fact, there's a whole field in computer science or theoretical computer science which is worried about this. It's called the partition function. Okay, this normalizing coefficient, and computing that is considered hard. Okay, but anyway, let's come back here. So because base rule, generally computing base rule is hard. Okay, unless for very simple cases it's easy, but in general applications, in general it's hard. Okay, for example, let's say p of x is a uniform distribution, okay? And this guy here, let's say this is the Bernoulli distribution. Okay? It just means that, hey, x is uniform. So you draw a sample from x. X happens to be 0.5. And data given x is, let's say x is 0.5. Then the probability of landing heads given the mean is 0.5 is 50%, right? So that's the likelihood model. For example, if x is 0.9, for example, x is 0.9, then probability of data given x or probability of sale given x is, is 0.9, right? So, so if you have a uniform distribution and a Bernoulli distribution, then it turns out that the posterior distribution is can be computed. You can always compute. You can always multiply things and compute the denominator and get the posterior distribution. Remember, if x is a uniform distribution, then you have x for every value from 0, 0.1, 0.2, 0.3, all the way to 1, right? So there is, you can always numerically compute this, but it turns out that for uniform or in general, this is also called a beta distribution. Uniform is not called beta, but uniform is a special case of beta distributions. Okay, beta distribution is a distribution over the interval 0, 1, just like a uniform distribution. If it turns out that if the prior is a beta distribution and the likelihood model is Bernoulli, then it turns out that you don't have to do any computation, to any crazy computation, like computing the numerator, computing the denominator for every x value to find the posterior. Okay, turns out that the posterior also happens to be beta. So this is a special property where if the prior happens to be from a certain distribution family, like beta distribution, and the likelihood happens to be a certain likelihood family, like the Bernoulli family, then the posterior also happens to be a posterior distribution also happens to be a beta distribution. Okay, that's called conjugacy. Or more formally, beta is called a conjugate prior to the Bernoulli likelihood. Okay, so the same idea is expressed here, where I'm trying to show that not for beta and Bernoulli, but for this is just the definition of, okay, let me just, but for a generalization of beta and Bernoulli, which is the generalization of beta distribution is called the Dirichlet distribution. We have talked about Dirichlet distribution when we looked at latent Dirichlet analysis. So beta distribution is a special case of Dirichlet distribution. Similarly, multinomial or categorical distribution is a special case. Sorry, categorical distribution is a generalization of the Bernoulli distribution. Okay, so so let's talk about conjugacy in their context, in a more general context, because beta and Bernoulli we already know them a little bit. So Dirichlet distribution, if you remember, Dirichlet distribution is is parameterized by some parameter vector, and it produces an output, and the output belongs to a simplex, in the sense that the output, if it's 3 dimensions or 10 dimensions, they sum to 1 and they're all positive. Okay, that means they're a distribution, right? So they sum to 1 and they're all positive. Okay, so it's a distribution. Remember, we did this for LDA. So if there's a distribution, given the Dirichlet distribution, okay, and there's a distribution explicit expression for the distribution itself, the distribution function. Okay, different x. I was using x there. Theta is the random variable here. The distribution function for any given theta or any given x is this very messy or very complicated looking expression. Okay, so you may ask, like, what is this tau and all that? There's a mathematical special functions. Okay, and just like e to the power x and so on. So there's special functions. Actually, the function definition is given here. So this is the prior. Okay, so this is the distribution. This is the beta. This is the Bernoulli. Sorry, this is the Dirichlet distribution, and Dirichlet distribution happens to be the conjugate prior for the categorical distribution. So let's this distribution we have already seen when we looked at LDA. So as I said, this is a distribution over the simplex Dirichlet. Okay, alpha 1, alpha 2, and alpha 3, because it's 3 dimensions. So yeah. So Dirichlet prior is as I said, is a conjugate prior to the categorical distribution or the categorical likelihood function. Okay, so a categorical or a multinomial. Okay, categorical and multinomial, there's slight difference, but you can interchangeably use them for our discussion. A categorical distribution is nothing but if you have, let's say, a die, right? A die has 6 faces, and each phase can happen with probability 1/6, right? So a die basically is an example of a categorical random variable. Okay, in the sense that random variable can take value 1 with 1/6 probability, value 2 with 1/6 probability, value 6 with 1/6 probability. So there are 6 outcomes. It's just a generalization of the two heads and tails outcome. Okay. So if you want to write that function, okay, write that likelihood function given a probability mass function. Let's say instead of 1/6, 1/6 for the die, right? Outcome 1, 2, all the way to 6. This is a categorical distribution, right? X taking value, and this is the probability of x, right? Instead of this, you can have any other probability mass function. Instead of 1/6, you can have 0.3, 0.2, 0.5, and yeah, this is just, I guess, 1. But if you had some other probability mass function, then the way to represent a categorical distribution is like this. You just multiply, you just say it's the probability to the power z. Okay, so where z is, z is just the indicator of whether that kth coordinate is 1 or not. Okay, so so what I'm trying to say is that probability of z given theta, okay, is nothing but equal to 0.3 if z happens to be equal to 1. Yeah, 0.2 if z happens to be equal to 2, and so on. So there's a little bit of abuse of notation. When I say z is equal to 1, I'm just saying that in the z vector, it's basically 1, 0, 0, 0. Okay, and in the second location, all I'm saying is z is equal to 0, 1, 0, 0. So this is the categorical outcome. You just think of a vector where the first coordinate is 1 if the first outcome happens, second coordinate is 1, so the second outcome happens. So this is the likelihood function. Okay, this is the likelihood function for the categorical variable. Now, given the prior and the likelihood function, if you multiply, so remember Bayes' rule, so we have to multiply the prior with the likelihood function and divide by the normalizing function, which is the likelihood of the data, right? Marginal likelihood of the data, marginal likelihood of z, or marginal probability of z. Okay, if you do that, yeah. So let's say we have many such data points, then you can always many such data points, then you can say, so this is actually equal to data for us. Okay, then the posterior probability or the posterior distribution over theta is equal to the prior distribution over theta times the likelihood, and there's a pi of n, which just means multiply n times because n independent trials, okay, n independent events, and then divided by the likelihood of the data or the probability of the data. So this is exactly, this is the likelihood, and this is the this is likelihood, which just means probability of data given theta. Okay? That's what this is. Now, if you compute this, it turns out, I mean, we're not going to show it, but it turns out that it has a function expression, has an expression which looks like this. Okay, so what is this? Is again a product over k over each of the k values, sorry, k coordinates or the k values that k coordinates of theta actually. And it turns out this posterior distribution is proportional to something. It's like a product of bunch of thetas. Okay, but you can see that the prior is also a product of a bunch of thetas. Okay, and in fact, it turns out if you really like compute this this right hand term expression, then it, because of this similarity of this functional form, you can actually say that the posterior distribution is also a beta distribution. So is also a Dirichlet distribution. Is also Dirichlet with some alpha nu. Okay, so remember theta is Dirichlet with some alpha, right? With some parameters alpha, right? Alphas in fact are here. This is also Dirichlet with alpha nu, where alpha nu is just this new alpha. Okay, so this is exactly, so instead of actually evaluating Bayes rule, you can just do, hey, if the previous alpha was some bunch of numbers, previous alpha 1, alpha 2, alpha 3, let's say 3-dimensional case, then alpha nu is again very easy to compute. Alpha nu 1, 2, and alpha 3 is just alpha 1, alpha 2, alpha 3, which is the old ones, plus the sum, this extra correction terms, some, let's call it C1, C2, and C3. So you don't really have to even apply Bayes rule. It's just that you're just directly working with saying, hey, if the previous parameters were alphas, if some outcomes happen, if some observations happen, okay, with some data realized, Z1 to Zn, let's say, then the new alphas, so then the posterior happens to be still a Dirichlet distribution, and I can just compute the alphas, the parameters of this distribution. I don't have to really, touch Bayes rule or do anything numerical here. Okay, so that's the idea about conjugacy, and this is something that you will try out in question 2 in assignment 4. Okay. Any questions here? Okay, if there are no questions, then let's in the next few minutes talk about contextual bandits. So to start to discuss contextual bandits, I want to talk about another algorithm. That algorithm has multiple, I guess, motivations, but I want to skip the motivations because it's just an algorithm for solving the multi-arm bandit problem. Okay, so we're going to start with that as a warm-up to talk about the contextual bandit algorithm, a contextual bandit algorithm. So we'll skip the motivation. So there's just motivation, which is not super important for us. We have already seen 3 algorithms, Epsilon-Greedy, UCB1, and Thompson sampling. There's a motivation for another algorithm, but which, the motivation is basically that it makes less assumptions, but we will skip that motivation and talk about the algorithm itself. Okay. So this is all, again, motivation. Yeah, let's talk about the algorithm. So this, again, you just have to think about this as a yet another alternative, just like Epsilon-Greedy. We can use this algorithm. This algorithm name is called EXP3. Okay, so these namings just come from generally the researchers name them in their works. So what does this algorithm do? Okay, so this algorithm saying, hey, if you have k decisions to make, capital K decisions to make, 2 decisions or 3 decisions or 5 decisions, then what you do is maintain weights. Okay, so maintain a number, a number for each of the k decisions, capital K decisions. Okay, And then what you do is create a distribution over these decisions, okay, a distribution over these actions. And how do you create distribution? You can just say, hey, I have a bunch of numbers. I can just do something like, instead of a softmax transformation, you can just simply do a normalization transformation, right? So these are numbers, but what I want is a distribution, okay, over these capital K actions. So what I can do is I can do W for the kth guy. I can do WK divided by W of all the other all the actions, okay, not just other actions, including this action. This ratio, okay, is just a normalization, right? So if you have a bunch of numbers 5, 4, 1, 2, then I'm just saying divide 5, 5 divided by 12, 4 divided by 12, 1 divided by 12, and 2 divided by 12. Okay. Um, so that's, so these are 4 numbers. If I do this, then I know that they sum to 1, right? This is just a simple normalization. I just need the numbers to be positive, and as long as I have a bunch of positive numbers in the numerator, I can always divide them and make them a distribution, right? PMF. Now, with what the algorithm does is also adds an extra offset, okay, so extra multiplier, and that extra multiplier is just to take care of again just to ensure that no action has 0 probability. Okay, so let's say if the W happens to be, let's say for one of them 0 instead of 5 5 4 1 2 5 4 0 3. Okay, so it turns out that if it's 0 here, it's 0 divided by 12. um, Turns out that if you just use these ratios as a distribution over actions, you will never try third action. Okay, so but you want to have at least some probability with which you'll try the third action. So you want to do that. So that's why you add for everything in offset, plus let's say 1 by 12 or something. So if you give everything in offset of 1 by 12, the sum is not going to be equal to 1. So to counter that, there's some minor fixes that have been suggested, okay, in this algorithm. But so that's it. So you're just ensuring that every action gets at least a minimum probability that will get picked, and beyond that, you're just maintaining a bunch of numbers. Okay. So at any given point of time, since you have a distribution, what you can do is sample from the distribution. Okay, sample from this distribution to figure out what decision to make. Okay, and this is again sequential decision making because these numbers W's will depend on what all has happened in the past. Okay, so W's depend on what all has happened in the past, and since W depends on the past, your action now depends on the past as well because your action depends on W's through this distribution. So how do these W's depend on the past? In the sense that how does W's get updated when some new information is revealed? So for example, you decided to make a decision number 1. Okay, so you try action number 1. So if you tried action number 1 and something happened because of that, maybe you made 100 sales or 50 sales or whatever it is, then that has to be updated in an improved W. And the intuition is that, hey, if I make if I get higher reward for action 1, then W1 should increase, right? So that's exactly captured in this update idea, where what you do is you, at any given point of time, you would get a reward, right? So at any given point of time for every action k, let's say every action little k, you would get a reward, right? You'll get a reward. If you don't play that action at a time t, you can just think of the reward to be 0, right? So this extra term here is just saying indicator of whether you played that action k at time s. Okay, so at every time s, so let's say, let me put a simple example here. So reward for action A, reward for action B. Let's say we only have 2 actions. Okay, so s is equal to 1. Maybe I played action A, which means that I would potentially get some reward for action A. Let's say that is x1 of A. And action B, I don't have, I did not even play it, so I'll get 0. Then and at time 2, let's say I played action B, then this is definitely 0. Then and here I'll get x2 of B. Okay, those are the original rewards. What I'm also going to do is normalize. Okay, so let's call it x tilde. And tilde A and x tilde B. So x tilde A is going to be what is the probability with which you played action A? So let's just focus on one of them. So let's say x tilde b is just going to be x2 of b divided by probability with which at the second time instance you played b. Okay, so that's it. So that's x2 of x tilde of b, and similarly x tilde of a is going to be a similar ratio. Okay, so something divided by something. So and that's given by this expression. Once you have such an expression for every time period, what you do is w is just going to be a sum. W is just going to be a sum of these numbers for each arm. So for arm A, you'll just sum, for let's say for arm B, you'll sum these guys. So actually here it's 0. You'll sum these guys, sum, and then you just do an e to the power that sum. Okay, so that's what you see here. Okay. And so W is just what the intuition is that if you played arm B and you got a reward, then the sum will increase, and therefore W will also increase. W is equal to just e to the power that, so W will also increase. Okay, multiplicatively, and whereas the other W, for if you did not play, let's say, so there are going to be two. So there's going to be WA, and so let's call this WB. It's going to be WA, which is also going to be similar expression. Okay, now I have WA and WB. Now I can always create a distribution, right? So I'll just do WA divided by WA plus WB, WB divided by WA plus WB. This is exactly this expression with that extra offset. Okay, so I want to ensure that plus some gamma by k or something, plus gamma by k. And if it's had an offset, I need to have a multiplier, which is 1 minus gamma, 1 minus gamma. So this is the two probability values, okay, for the two actions that I have, given the reward that I got, given the rewards that I've got so far. Okay, so history determines W's at any given point of time. Given W's, you take an action based on W's by just sampling. Okay, this algorithm again does exploration exploitation, and it can be shown that this strategy also minimizes regret. Okay, minimizes cumulative regret. So yeah, I mean that minimizing cumulative regret is basically getting a curve which doesn't grow with the number of interactions. So x-axis is the number of interactions. If you're not minimizing regret, you're just doing worse and worse. Okay, if you don't figure out and zoom in and pick more often the best action, if you don't pick more often the best action, you're gonna lose, right? So you'll do worse than the best action, and since cumulative regret involves what is the best action in hindsight minus what did you do, so that gap widens and widens if you don't pick the best action more and more often as a function of the number of interactions. Okay. So any questions up to that point? That was so the reason why I introduced exp3 is to talk about another algorithm for the contextual bandit setting. So what I'm going to do in the next few minutes is define, or at least mention, what is the contextual bandit problem, okay, and then a solution. So actually, that's what we're going to do. So what we've done is for multi-arm bandit problem, we have 3 algorithms, right? Epsilon-Greedy, UCB, and Thompson sampling. And this is the 4th algorithm, which we just talked about. So this is the first part. Second part, contextual bandit problem, we'll also see a solution. In fact, it's going to be called exp4. Okay. And the third part, we're going to talk about the reinforcement learning problem, and we'll only see a solution, which is going to be Q learning. Okay. And Q learning is something we'll see later anyway, and that's and a neural network enhanced version of it is what we will do. We'll be using in assignment 4. Okay, question 3. Just to give you a context, and these 3 are related to assignment 4, question 2, and as well as question 1, I guess. Question 2 and question 1. Okay. Just to give you a sense of how things are. Any questions up to this point before I talk about contextual learning problem and its solution? Yeah, if you're not following something or something is unclear, please do ask, because I'm moving forward. And without feedback, it's hard to figure out which part is tough or unclear to folks. Okay, so let's talk about bandits with context. Okay, so and it's best motivated using an example. So I've been talking about website A, website B, sale, and so on. Let me actually talk about a specific application that folks at Microsoft tried out with this idea, with the ideas that we have seen so far. So in particular, let's talk about the um, um, the news personalization problem. So msn.com is a web property, I think, where you get to see news articles. Okay, so here the machine learning problem, or the decision making problem, is to personalize the news stories to the users. Okay, so user arrives to this web property, to this website, but when they arrive, they generally have information. So the website has information about them typically, okay, which is their browsing history. Maybe they're already a Microsoft user, so they'll have a user account and previous visit information and all that. Okay, which articles they saw before and all that. Okay. Based on that information, Microsoft's website, this website, Amazon.com, wants to personalize the story shown to this user. For example, this user may be mostly interested in sports, and it doesn't add value to show information about music or some other current events and so on. Okay, so Microsoft chooses stories, and then once Microsoft shows, once the page is loaded, then the user responds, right, by clicking, navigating, spending time on this website, and so on. Okay, so this keeps happening in a for loop, right? It's user comes with their information, you take a decision, and then the user responds by rewarding you by spending more time on your website. And then again, a new user comes. This user, second user, may have a completely different context, and so you want to show a completely different set of news stories to them, and so on. Okay, so that's the practical application where they've actually employed one of the or this is actually several years ago, 5 years ago, and they used Epsilon-Greedy, or a variation of Epsilon-Greedy, to show improvements in click rates. Okay. So, this is a motivating example for contextual bandit problem by making the following assumption. Okay, so the assumption is that recommendations to one user do not affect the other users. So user one comes, I show them something. User one comes with their context. Okay, with their context just means this information. Okay, the browsing history, their profile, and so on. Okay, that's the context. That's just another name for a state or a feature vector. Okay, I'm going to use the word state because we're going to talk about again state in a few minutes from now. So user comes with their state. Okay, the state is just whatever we know about them. Okay, and given that, and the key assumption that we're going to make while figuring out a policy. The policy is just given this user state, determine what to show. Okay, determine what to show. There is some bunch of news articles to show. That that's the decision to make, right? The assumption is that when I show something to this user, the next interaction, maybe with another user, maybe with the same user, this user doesn't remember, the the second time I interact with another user, it could be the same user, it could be a different user, has nothing to do with what happened in the previous interaction. Okay, I mean, for another user, it makes sense, right? If user one comes and I show them a bad bunch of news stories, or suboptimal bunch of news stories, and they leave the website immediately, the next user who comes in, they have nothing to do with the previous one, right? So there is no temporal impact in some sense. If the same user comes, there also we can always make an assumption, which may not be true. We can always make an assumption that this user saw the previous recommendations that have no influence on them, how they will reward me the next time I show another bunch of recommendations. Okay, so that is of course may or may not make sense in certain applications. But that's the assumption. With that assumption, we can talk about the contextual bandit problem. So basically, what are we adding to the previous discussion on multi-armed bandit problem? So why is this not a multi-armed bandit problem? It's not a multi-armed bandit problem because there's an extra thing, which is the context or the state. Okay, so previous all the solutions that we saw, Epsilon-Greedy, UCB1, and all that, they don't have a user. User is not coming with their user profile. Okay, so it's just you take an action at every period, something happens. Okay, it doesn't depend on if user you come to the website or I come to the website. So this is what we're going to fix now with contextual bandits. I'm just using the word, acronym CB to represent contextual bandit. this carryover effect, which is also not present in the previous Bandit solutions, is the effect that one interaction may have an impact on the next interaction. So if user signs up on my platform, let's say I'm Netflix, and I show them completely wrong genre of movies, the next time the user comes on the platform, they will have that information, right? So they remember that, hey, this service is probably bad, and so next time when they respond, they may not they may not maximize your KPI. Maybe your KPI is to make them use the service for a long time, right? Make them watch much of the content on your service. There may be carryover effects, okay? And so that is not captured in contextual bandits, but we'll capture this carryover effect in the full-fledged problem, which is called a reinforcement learning problem. So from one interaction to the next, there is no relation currently. Okay, so that's contextual bandits. If there is a relation, we're going to look at reinforcement learning to deal with that. Okay. As I said, in this problem, we get a context. We want to find the and our objective is to find the best policy. Okay, not the best action, but the best policy. Not the best single decision like A or B or C, but a policy. Why a policy? Because every time a policy is basically a function. Okay, given a context, it produces some action. Okay, so we need to find F rather than a optimal action. Okay, so that's the I guess non-triviality with this I guess more complex problem. And the thing is, we will not see the same context twice. Okay, so for example, in the multi-armed problem, we can take actions A again and again and again, get a feel for the average statistic for average performance statistic for action A. Here, context may not repeat, so you don't know if context repeated. Then for each context, you could have just run a multi-armed Bandit algorithm, right? If the same context, if the same user comes like 100,000 times, then yeah, you can figure out what is the best thing to show to them. But if the user comes like once or twice and that's it, then it's hard for you to figure out F. Okay, and yeah, and the objective of contextual Bandit is to figure out F again, minimizing cumulative regret. So we want to minimize still cumulative regret. Okay, but we want to work with policies. We are using the word policy. Policy, just think of it as a function which goes from context or a state to an action. Okay, and that's literally what policy is. Even formally, a policy is just a mapping or a function from states to actions. Okay. Okay. So what is the utility of having a context, and how can we, like how do we solve this problem? We're going to use, as I said, we saw EXP3 before. We're going to extend EXP3 to an algorithm for solving contextual Bandit problem. But what is the key idea? The key idea is this, right? So X is the context. There could be many, right? So if there's so many contexts, then it's hard to, for each, if there were like 10 different contexts, so for each context, you can always, as I said a few minutes ago, you can always run a multi-armed Bandit strategy and figure out what is the best thing to show for this context. So for what is the best thing to show for X, maybe some A, maybe what's the best thing to show for some X prime context, maybe some A prime, but you can't do multiple multi-armed Bandit strategies, because same context may not appear at all, right? So if X is too many, then there's a problem. You need to somehow, extrapolate from X to what is the best thing you could do for X prime. Okay, and that's exactly what a function can help you do. Exactly what a function can, a policy can help you do. If two contexts are similar, maybe you want to show similar actions. Okay, maybe you want to take similar decisions. Okay, so that's the first thing. And the second thing is this F, right? So maybe there are many choices, F1, F2, F3, F4, so many policies from which you can pick, you want to figure out the best policy. Okay. For example, they need not be even finite. For example, if you think of a linear function class, then there are a million or a billion or there are infinite number of linear functions, right? So again, this is many. So the idea is, if you get, let's say it turns out that maybe you picked the first policy, the first policy recommended action A. The key idea with the contextual bandits, the clever idea is that if you took a policy, some context X came, you picked a policy F1 somehow, and it took an action. Sorry, it took an action A. Okay. Now what you're going to do is you took an action A and it gave you a reward, some reward R. Okay. Now this reward R, of course, you're going to ascribe to how good this policy is, but you can also, the whole key idea is that you can also ascribe this reward to maybe some related policies. Maybe function 2 is not very similar, not very different from function 1. Then you can also say, hey, function 1 got high reward, maybe function 2 can also get high reward. Okay? And the same idea. So if this reward you get for a context X, then maybe you can also get a similar reward for very similar context X prime. Okay, so that's somehow you want to kind of use some sort of neighborhood effect, and that's the whole point of supervised learning, right? So you want to generalize, you want to extrapolate beyond what you see in your data, right? So let's discuss that with a very small example. Let's say we have 5 ads. Okay, these are 5 actions. Okay, let's say we have 5 actions. Yes, these are the actions. And let's say we have 4 policies. For simplicity, let's say we have 4 policies. It could be 40 policies, it could be a lot more, but let's say we have 4 policies. Okay. What do these policies do? Given an X, it will say, hey, show and add A. So if some user profile comes, first policy will say, hey, show add A1. Maybe second policy says, hey, show find local florist. Okay. Right? So these are the policies. Now what we'll do is, we have policies and then actions, and we also have context. So what we can do is think of applying EXP3 at the level of policies. Okay, since there are 4 policies, we can maintain 4 weights. Okay, so as if we have 4 actions or 4 meta arms. Okay, and we can think of EXP. We can try to apply one round of EXP3. Okay, so let's say in round T, let's say each of the policies recommends something. So let's say policy, instead of F, I'm using E. So policy 1 chooses action A2. Policy 2 also chooses A2, and the other 2 policies choose A4. Okay, and let's say, so these are the choices that each of the policies would make. Now, since we are running EXP3, the algorithm, it will choose one of the policies. Let's say it chooses policy 1, okay, with some probability. Remember, there's a distribution over policies, 4 policies, and you pick policy 1. Okay, you pick the policy 1, and policy 1 is saying, hey, show add A2, and you show add A2, and it got clicked. Okay, so you got a reward, which is, let's say, a reward is +1 for this action that you took. Okay, you took policy E1, and you for that you got a reward. Okay, so what you can do is you can assign a reward to policy 1. So you can the same number, the calculation that we saw earlier. So you get the reward divided by the probability with which you took that policy. Okay, and EXP3 naively, if you applied, you said, hey, all of the policies, the reward should be 0. Okay, because they are unrelated to this. But clearly, you can see that even if you had picked policy E2, you would have suggested the same action, and therefore you might have gotten the same reward, right? The same click, right? So the idea with the contextual bandit solution strategies is to this generalization. So hey, it's not just E2 was also recommending A2, so let's also say that E2's reward is not 0, but actually the same as E1. Okay? So you're going to improve the assigned reward, which is not 0 for E2, and then continue to play EXP3. So that's the idea of trying to generalize from what interactions based on interaction data that you're seeing. Okay, because if you only rely on interaction data to only update that policy or only update that action, then you have so many other policies and so many other contexts that you will never see. So you have to somehow generalize. Okay, so that's the key idea behind many of the algorithms that are generally proposed for this problem. So in terms of algorithms, it's exactly the same. It's called EXP4 because there's extra actions and there's also policies. So what you do is maintain weights on policies. Okay, so pi is a policy. So for example, E1, E2, E3, and E4. Each one will have a weight, W, these Ws. Okay, because there are weights on policies, one intermediate computation you can do is from weights on policies, you can also get a weights on a bunch of weights on the actions. Okay, so what are weights on actions? Weights for action, let's say A2 is equal to W of E1 plus W of E2 divided by W of E1 plus W of E2 plus W of E3 plus W of E4. Okay, that's because both these policies, E1 and E2, are suggesting A2. Okay, so for this given context, so XT is the context, right? So and so probability of A2 is this, probability of A4 is the opposite, okay, and probability of A3 and all the others is 0. Okay, so that's the distribution you can compute over actions if you know the weights over policies. If you know the weights over policies, you can always compute the weights over actions by doing this, aggregating this way. Once you have the weights over actions, you can always sample from that. Again, you can always add an offset so that every action has at least some probability of getting clicked. Okay, that's just shown by these extra terms here. Let's not worry about it. Yeah, you pick an action from this distribution or actions that you have just constructed and observe a reward. And now given this reward, you can always update the weights over the policies. Okay, so every policy that suggested this action, you improve the weight. Okay, so you improve the weight. This is exactly the same as what we're doing in EXP3. And for everybody else, there's nothing to improve because the reward is 0 for them. Okay. So any questions here? So this is pretty much the N algorithm for the contextual management problem.
Hello, Professor.
Yeah.
I have a couple of questions. So, like we mentioned, our motto for all algorithms is like generalization. So, suppose if we have 1,000 contexts, we might just have like 20 policies, which will address all these 1,000 contexts, something like that.
Yeah, generally you don't even need 1,000. It could be infinite number of contexts. So think of feature vectors, right? So you would not, if some coordinates of feature vectors are not finite, right? So for example, so then the number of contexts is not 1,000 or anything, right? It's just infinite number of contexts. Similarly, policies, if you think of the linear function class, policies are just functions. So if you think of the linear function class or something like that, then there are also infinite number of them, right? Still this algorithm, so this exp4 will not work because you have to maintain a distribution over each policy. So if you had finite number of policies but infinite number of contexts, that's fine. This algorithm would work. But if you don't have a finite number of policies, then this algorithm will not work, right? Because I have to maintain a weight over each policy, and I cannot even enumerate them. So
yeah. So like in this case of this contextual bandits, we need to have like finite number of policies.
No, that's not the case. I only showed an algorithm which works for the finite number of policies case.
Okay.
So I want to switch over. So I want to talk about infinite number of policies case, and actually I want to make a connection to supervised learning. And this is the first. This is one example. I'm again going to make connections to supervised learning and reinforcement learning in a few minutes. So for that, let me actually share my screen. Yeah. So the connection is you can actually get that connection from this paper instead of me. So this paper is a paper by some folks at Microsoft. So it's linked on the chat. So what I want to show you is how do you solve contextual management problems when you have an arbitrary number of contexts, like an infinite number of contexts and also infinite number of policies. Okay. So for that, so I'm not going to read all this, don't worry about all that. So let's focus on, so I'll strongly suggest looking at section 2.2 and introduction section of this paper. It's a really nice quick introduction to how contextual management problems are related to supervised learning. Okay. But what I want to focus on is just this number 2 here. Okay. So number 2 is some minimization problem, right? So it's saying, so here actually this F is a policy. Okay. So what we're trying to do is trying to figure out X is a context. Okay. In this, I'm just trying to parse this expression right now. X is a context, A is an action, F is a policy. You can think of it as a policy because what this policy is trying to do is for every action and context, it's giving a score. Okay.
Okay.
So I mean, either you can given a context, you can give, let's say, 10 scores if you have 10 actions, or you can also pair them together and say, hey, for this pair there's some score. Okay, you can do that.
Okay.
So this is giving a score, and the score they're trying to match it to the actual reward. So YT is like a reward that you would get. Like if you played action A, let's say YT, for example, could be 1 if a sale happened, or YT could be 0 if a sale did not happen. So what this way of doing is, in equation 2, they are saying if you have collected data, you can actually solve a problem which just looks like regression. Okay, so you can actually try to find a policy. This is argmin minimizing a loss function. They just define a loss function over the historical data from t is equal to 1 to how much ever data you have up to this point. Let's say you're just solving, try to find the f such that f is producing scores which is predicting reward, which is the actual reward. Okay, so you can actually just use all the ideas from supervised learning to also solve contextual bandit problem. Okay, but I don't have time to get into this because we're gonna anyway look at a more general version of the contextual bandit problem, which is reinforcement learning problems, which we'll do right after a break right now. But this is one way to solve, but contextual bandit problems have their own set of issues. This is one way to approach. Okay, this is just a informal way of saying that, hey, you can actually use supervised learning approaches. In this case, I mean, he's saying regression approaches. You can apply regression approaches to solve for the best policy. Okay, but there is extra care that needs to be taken care of because the data set is not supervised learning data set. The data that you're collecting depends on the actions that you took, and the actions that you took depend on the previous data. So the data is not independent or identically distributed. It could be identically distributed, but it's not independent.
Okay. Yeah.
That is a major issue that we are kind of glossing over. We're going to look at that issue maybe when we talk about reinforcement learning in a few minutes, but that's the biggest issue. If the data was independent, then you can just think of it as a supervised learning problem. Okay? And they're saying even if the data is not independent, you can do something like supervised learning, but you have to take a little bit of more extra, I guess, precautions, and that's where this weighted least squares loss is coming. These weights are going to depend on maybe can address that dependence issue in some way. Okay.
Oh, yes, got it. Like how our dependent actions are based, we are going to choose our weight based on that or something.
Yeah, yes. The weights are just going to address the issue of the data being dependent data. Yeah. Okay. I mean, I'm not going to explain more than that because I think that requires its own some amount of detail. Maybe we can talk about it after the session.
Sure.
Yeah. Yeah. So with contextual bandits, I just wanted to motivate the problem and give an example solution which follows a similar ideas to multi-arm bandit problem. But that only works, of course, as you saw, as I just mentioned, it only works for finite number of policies. Infinite number of contexts are fine. Whereas if you had infinite number of contexts, this paper is just an application paper. It's proposing something new, but it also summarizes nicely what are the different what are some examples of different contextual bandit algorithms. Okay, so you can look at the first two sections at least to get a feel for different solution approaches. And this is exactly what people did, for example, for the MSN.com application. And this is what they would do for many realistic applications and mostly in internet problems. Okay, so what I'll do is let's take a break for 10 minutes and resume at 7:51. And I'll pause the recording now. But if you have questions, I'll leave it on the chat, and we'll also take some questions and discuss more after the session. Okay. Okay. So welcome back. Before I again get into some of the basics of reinforcement learning, which is the next topic, I wanted to quickly show you some motivating things instead of going through a slide. The slide deck also has a few motivating examples, but I wanted to show you something with using the browser. So yeah, so as I said, I mean, this is a link I had shared earlier in the session. So this is just a, I mean, there are many such lists, but you can look at um, um, you can look at this list to get a feel for what you can do without even knowing about the tool, which is reinforcement learning. You can click on these things called environments, and we're going to talk about what is meant by an environment. You can look at some of these links, and I've actually opened a couple of them. For example, you can look at this called Open Source Simulator for Autonomous Driving Research. Okay, this is the simulator here. It's a simulator that's for by Intel and some other Toyota and other companies, which lets you, for example, use reinforcement learning as an idea to do, for example, autonomously drive. So, so you can see that there's a simulator for you to train an autonomous vehicle. Similarly, there is a simulator, another link called Deep Drive, which also lets you build a self-driving AI, and you can actually use these. You can use reinforcement learning ideas to build your own self-driving car. But I mean, of course, there are a lot more complications to self-driving technology than this. But and on the fun side, there was actually a competition, I think, a year or two ago, and this is related to that. It's called MineRL. So it's basically, creating an agent, creating a piece of software which navigates through the Minecraft, world, and does these types of operations like navigating, obtaining objects, and surviving and doing things. So even this can be done using AI or whatever, reinforcement learning. Okay. And finally, GEM is something that you'll use as in question 3 of assignment 4. So in particular, you'll exactly use this cartpole environment. Okay, so this is a yes, the previous one was the cartpole environment. There are other ones, pendulum and so on. So these are all environments. Okay, these are all situations where you want to make decisions. You as in you want to make the computer make decisions. Okay, for example, many of these games that you see on the right hand side of this page, this is enabled by the software. But you can imagine if you can learn to make decisions in the simulated environment, you can also probably make decisions, hopefully, in the real environment. Okay, but so this in particular, the one you just saw, balancing a pole, vertical pole, is exactly related to the question 3, okay, in assignment 4. So I wanted to quickly show that before I switch to the slide deck. And if you have questions, please ask.
So, Professor, question not on this, more so on the slides or the PDF.
Yeah.
Did you move the location? Chaitanya pointed out to me, and even I'm getting the same error. It says the item is deleted. Only the annotated slides are available. That takes us to the OneNote.
Okay.
But then the link to the slides says item is deleted.
Okay.
Please check and
yeah, that's a good point. Let me double check that. So let me. Yeah, that's a very good point. Actually, I didn't delete it. I mean, it might have moved in the Dropbox location. So okay, I'll fix this right after this. Right after right after the break, not break, but right after the session. Okay, good point. Thanks for pointing that out. Yeah. So with what I wanted to do was the first bunch of slides in this slide deck. So we are actually on module 1011, but the module numbers are not critical here. So we're gonna move to the next set of next I guess idea in this I guess course of going from predictions to decisions. Okay, and predictions to decisions is not something that you will see that often. So that's why this is the previous session and this session. And hopefully the next session will cover how you can go from predictions to decisions, and sometimes it's very tightly coupled. And in reinforcement learning, you'll see that predictions and decisions are very tightly coupled. Okay. So today's out. I mean, for the rest of this, I guess, session, we are basically trying to scratch the surface of the basics of reinforcement learning. Okay. So although I showed you earlier all these examples with Minecraft or with self-driving, and so on. So that's, I think one stage away. In fact, in assignment for question 3, you will scratch, you will try out something in particular from the OpenAI's GIM package to balance a pole on a cart. Okay, so this literally, the pole is going to fall down. You want to go left and right so that the pole can be balanced, and that's what you'll try to do. And that's an example, but you can, same ideas apply to all these other complex situations, and not just for driving our games, but also for inventory management, for stock, trading, and so on. So you'll see on the resources page that I linked earlier, right? The RL Wiki GitHub page. There are a bunch of links, and it'll be useful to just go through them to get a feel for what applications can use this technology. Okay, the technology is not yet mature, unlike supervised learning. I mean, relatively speaking, but still, it's a very interesting technology to know about. Okay, RL. I mean, the solutions in the RL for the RL problem. So we'll actually skip this motivation section and directly get to RL basics, and hopefully we can get to either MDPs or to define this new object called value function. And the value function idea is going to help us in defining our only algorithm. So in fact, for RL, we only look at one algorithm called Q-learning, and its deep learning extension called deep Q-learning. And deep Q-learning is exactly assignment 4's question 3. So we'll only look at one algorithm, but there are many algorithms. Okay, many researchers keep suggesting new algorithms adapted to different situations, and taking advantage of the structure in the application and so on. But we'll not look at many of these other variants. Okay, we'll look at one prototype solution strategy, okay, which is based on this intermediate idea called value functions. Okay? So with that, let me get started. Let me scroll over motivating ideas. So this slide gives you an overview of what is the relationship between the 3 problems. Okay, so the multi-arm bandit problem, it's saying take an action, get a reward, and try to figure out which action is the best. Okay, so all these 3 problems, by the way, multi-arm bandit, contextual bandit, and full RL of reinforcement learning problem, all have the same idea: collect more and more rewards. Okay, but you don't know anything about how to collect more rewards, because you don't know which action is the best one. So you want to figure out which action is the best, or what to do in a given point of time, so that you can collect more and more rewards. Okay, that's the problem. And multi-arm bandit, we just saw, hey, try action 1, try action 2, and maybe be greedy, or sometimes explore. We saw several algorithms there. And contextual bandit, the idea is, given the state or given the context, there's a policy, F or pi or whatever you want to call it, E, whatever you want to call it, that maps to an action. It gives, hey, given this context, let's take this action. And that action and the context both together determine the reward. Okay, so for example, if you showed sports stories for somebody who's interested in music, then the reward you get is there's no clicks. In fact, they'll close the window and go to some other website. Right. So the reward is determined by both action and state, and that's about it. But the full reinforcement learning problem involves the following extra arrow, which is that you see a context, you take an action, okay, and action influences what's the next state you will see. Okay, and that's very clear for self-driving, right? If you are at a 4 crossing or intersection, and you take a left action, okay, then it's very clear what the next state is going to be. You're going to be on that left road wherever you took the turn, right? If you take straight action, you would be crossing the intersection and will be on the same road. So what you will see in terms of state, think of the state as what you're seeing in the front, I guess, from the front window. It's just going to depend on what action you took right before, when you cross the intersection, right? So actions determine the next state. Okay, it is not the case for contextual bandit. And again, actions and the states together determine reward. And I also put a bunch of dots here in the sense that these rewards may not be immediate. In contextual bandit, you show a bunch of news stories, but as an example, and the user may click and not click and navigate away, right? Immediately. So things happen immediately. In the reinforcement learning problem, you take an action. For example, in self-driving, you took a particular exit. Okay, that exit determines how quickly you'll reach a destination. Maybe you should not have taken that exit. Okay, so the taking an action now has a long-term consequence on whether you'll reach a destination in time or not, for example, right? So that long-term consequence of actions is also interesting, is also a differentiating feature from the contextual bandit setting. So the two differentiating features: actions influence what happens next, or what context you see next, or who comes next. Same idea. And the second thing is actions that you take today have a longer term consequence, can transpire into getting huge rewards 10 years later, right? Like, for example, you doing this course may have a huge reward 5 years later. Okay. So but keep the chat open in case. Yeah, if there are questions at any point, please feel free to type it in the chat or interject me. So the RL problem, again, is a sequential issue-making problem. And the characteristic, as I said, is all about you saw the history of what all happened in the past. That should determine your next action. Okay, so you want to go from history to what to do next. Okay, so that's sequential decision-making. The key ingredients are an environment. Okay, environment is everything that is relevant for you to take a decision. Okay, what you observe, the relevant information that you observe for you to make a decision. That's what an environment is. Okay, and an agent is you, as in for example, if it's an artificial agent, software, an AI agent, it's all the same thing. Okay, agent takes actions. Okay, agent takes actions within this environment. So when, like for example, in self-driving, the car takes left and right turn within the environment, which is for example, simulator or in the real world, right? So that's the real world or simulator is the environment. The agent is the car, right? Or the software in the car actually, and the action influences the future. Right, so if the car takes a left turn or a right turn, it influences what's the next state of affairs. Like you're on street number 1, now you're on street number 2, right? And also, agent gets a delayed feedback signal. The feedback signal is what we want to say is the reward, and we want to maximize total reward. Okay, we want to maximize the total reward. So we keep taking actions over again and again and again, and for the rest of most of the session, we're going to talk about discrete time. So we are only taking actions every second. Okay, not like second 1 and then 1.2 seconds later and so on. So just discretize time as like second 1, second 2, second 3, second 4, or minute 1, minute 2, minute 3, minute 4. So we want to maximize total reward across all these minutes. Okay, over which the agent interacts with the environment. Okay, so maybe initially when the agent is new to the environment, it doesn't know what to do. But maybe after experiencing different, taking different actions in different states, different situations, maybe the agent can figure out what's the best thing to do. Okay, that's the idea. Okay, so what's the environment? As I said, the environment is, it sees agent action, and now we are talking about symbols. Now the symbols are we gonna use repeatedly, so do pay attention. So we're gonna environment sees agent's action AT and spits out. Just think of environment as an object which says it sees input AT and produces an observation ST plus 1, or state ST plus 1, or a feature vector ST plus 1, okay, or a context ST plus 1. All these mean the same thing. Okay? Produces an action, produces an observation ST plus 1, and also produces an immediate reward RT plus 1. Okay, so ST plus 1 and RT plus 1. At time t, agent took an action AT, and they saw a new state ST plus 1, and they got a reward RT plus 1. And that's about it. And many of the times we'll say the environment is Markov, in the sense that the environment going from state ST to ST plus 1 only depends on state ST and not the previous all the states that have transpired. So for example, the self-driving car, let's say at the intersection, it doesn't depend on whether it came from a highway or from a some other street. It just depends on that it is at the intersection. It taking the next state just depends on that it is at some portion of the intersection. Okay, so it's just called Markov property or memoryless property, that you don't remember everything that transpired to say what the next state is. The previous state completely captures everything about the situation, which can tell you what the next state could be. Okay, and that's how the environment will behave. So the environment will just depend on what the previous state is to say what the next state is. Okay. And what does the agent do? Agent, as I said, is just keeps taking actions. Okay, so keeps taking actions. And the agent's objective is to maximize reward. So it's like the maximize the expected total reward. Okay, we're gonna add in randomness here or make the rewards random variables. Okay, and so agent's objective is to, at let's say time t, you want to take action at, and time t+1 you want to take action at+1, and so on. You keep, we want to figure out what is the sequence of actions that the agent should take. Okay, and the agent wants to maximize this expected total reward. Okay, and now you can see there's an extra parameter. This is just a discount parameter. It's like time value of discounting, if folks who are in finance may know this, but basically you care more about the reward today than the reward tomorrow. So this extra parameter is, just think of it as like 0.9 or something, some discount. That future reward, I'll just discount it by 10%, okay, if I want to consider it now. So this is what the agent wants to maximize. Okay. Yeah, and the point is that, and the non-triviality is that the agent may trade off current reward to gain more rewards in the future. Okay. For example, think of the car situation. The car can wait in a certain lane for a long time. Okay, so losing time, but that lane may lead to a highway where you can eventually maybe later on speed up and therefore get to your destination faster. Okay, so there's a long-term consequence of the action that you're taking now. So the action of you taking now, which is to wait, may incur a penalty because you're losing time if you're in a queue in a certain lane which goes into a highway. But once you get into the highway, maybe you're super fast, so you're actually gaining reward. Okay, compared to maybe a different lane where there's no queue up. Okay, so so that's one feature that the agent should consider. And you'll see that all these can be taken care of in a purely data-driven way by when the agent learns a good, agent learns what to do in every situation. Okay, that's what the reinforcement learning problem is about. And similarly, that was the same problem with even contextual bandit. In every situation, every state, what is the thing that you need to do? What is the action that you need? What is the action that you need to take? Right. What is the reward? A reward is, we've discussed reward several times. A reward is just a scalar signal, and it just indicates how well the agent is doing at a given time step. So it's the immediate reward. Okay, and cumulative reward just means the sum of these guys. Okay, you want to take actions which keep, which get rewards to you, right? And hopefully the sum of these rewards is the highest. Okay, and reward hypothesis is just saying that every problem, every problem you can somehow massage it into saying that you want to maximize certain type of reward. Okay, so all objectives or all goals can be defined as maximizing of a certain cumulative reward. Okay? And this is, just a way to say that every problem you can always define a numerical number. Like, for example, if you reach the goal, that's the best. Reaching the goal will have a high reward, and not reaching the goal, you can always ascribe numbers which are, let's say, worse. In that sense, you can always ascribe these numbers to determine, to map to, you can always define these numbers such that the agent, by looking at these numbers, can figure out what's the best thing to do. So, as in, agent can determine, agent can reach the goal. Okay, that's just the reward hypothesis. I mean, it's not super critical to for us, but I guess the super critical thing is this: a reward is just a number for us. Okay, it's in fact a random variable at every given time step, little t. As I said, we want to maximize the total future reward. Okay, so at any given point of time, I want to maximize the total future reward. And as I said, actions may have long-term consequences. Then this is exactly, actions may influence the next state that you'll see. Rewards may be delayed. So action that I take now may lead to something awesome. I get a lot of rewards later, or I could, do badly. So there could be a long-term impact of what you do now. Okay, and I didn't, examples. We have already seen examples in the when we looked at different environments. So let me not motivate this. Okay, so in terms of pictures, what's happening? So agent is there. So just think of a function. So there's two functions or two objects. Okay, if you want to think of Python functions, and the agent sees state st and rt. Okay, maybe at the beginning you see a state, maybe rt is 0. That's fine, and you see the state st. Okay, it's a feature vector. Think of it as feature. All the measurements that you can see, like for example, the camera frame. If you are in a self-driving car which uses camera as a modality for taking input, okay, taking measurements. So you see the camera frame or the image. Based on that, you take an action, maybe press accelerate a little bit or turn left, turn right, or whatever. And based on that, the environment takes the action. The environment takes the action, and the environment responds back with saying, "Hey, now the new state is this," and you get an immediate reward, which is this. Okay, and given the new state and the reward, again the agent is going to take an action sorry, AT plus 1. Okay, and given action AT plus 1, again the environment responds by saying ST plus 2 and is your new state or new observation, and RT plus 2 is your immediate reward. Okay, and that's it. That's the interaction between agent and environment. Okay. Okay. So with that, let me quickly mention the difference between supervised learning and RL. By the way, when we were talking about contextual bandits, I use the expression f, x, and a, right? So this should be very similar to like y is equal to f of x. It's exactly what we do in supervised learning, except that in supervised learning we would have x comma y pairs, right? So some bunch of these xi, yi, I is equal to 1 to n or something, some bunch of training data. Okay, x could be images, y could be labels, and you just do image classification, right? So that's what you do in supervised learning, and this data is also generally IID. Okay, in the sense that there is no relation between one observation, one pair of observation xi, yi, and another pair of observation xj, yj. Okay, so you can permute the rows and there is no impact. Okay, it's the same thing, unless it's a time series. If you permute the rows, it's not a good idea. And if you think of contextual bandits, it's the same. It was almost the same expression. It's except that instead of y, class labels or something, I was saying actions, decisions are what you need to predict, or what you need to suggest. Okay, it's a mapping. So the policy was a mapping from context or state to actions, right? So even here, you are actually, when you say historical data, you would have the same type of thing: xi, ai, xi, ai, x1, a1, x2, a2, and so on. I is equal to 1 to n, right? It's almost the same thing, except this data is not IID, right? Because when I take action AT, it depended. It may or may not depend. If you make an algorithm which is like randomly flipping coins and picking an action, then it of course doesn't depend on history. But typically AT depended on history. Okay? In fact, the data is not just this; it's also rewards that you get. Okay, it's the context, the action, and the reward that you get. Okay, so xi, ai, yi, sorry, ri or something. Okay, so it depended on history. So in that sense, it's not IID. So what was the fix for that? We actually did not go into details there. I mean, I would suggest looking at that contextual bandit bake-off application paper if you want to look at just the intro section to get a feel for how it's addressed. We looked at one algorithm where the number of policies, the number of Fs were limited, so you could use the EXP4 algorithm. Okay, but the same issue persists even for reinforcement learning. So reinforcement learning, what happens? Input, right? So let's say X or state ST, X or ST, whatever you want to call it, and then an RL you want to produce an output which is AT, right? And you pass it to the environment. Environment produces ST plus 1 and RT plus 1. RT plus 1 is the training signal that you want to use, along with this information into the RL algorithm. So you use the state, you use the previous information, you keep collecting it, and you want to produce better and better actions. Okay, so that's what. So that's how it's different from supervised learning. Okay, in these respects, and yeah. And you, but in terms of, but there's also similarity, right? The similarity is exactly this, that you want to get a mapping or a policy from which goes from states to action. So in that sense, you are trying to find a function. And so the underlying optimization problem may look similar. It depends on what we do. And we'll see in DQN, it turns out that we will actually be solving some sort of a supervised learning problem at every time step. Okay. So.
Professor?
Yeah.
Can you repeat the difference once again? The difference between reinforcement and supervised, the last point.
Yeah, I mean, so to know the difference between supervised learning and reinforcement learning, first you need to know what's the difference between contextual bandit and supervised learning, because that itself captures the issue, right? So the issue is actions depend on history. which means that the data is not IID. So the third action is not independent of the second action and the second observation, and so on, right?
Yeah.
And also the action influences the next xj that comes, okay, xt plus 1 that comes, right? So the data is not IID at all. That's the first thing. If the data was IID and if you had to find a function, you can always do supervised learning style approach, right? We know how to do it, right? We know xi yi pairs, they are not related to each other. Observation pairs are not related to each other, or examples are not related to each other. Then we can just fit regression problems or classification problems exactly the way we have seen before. Okay? In contextual bandit, it's not the case. In contextual bandit, the only thing is that doesn't happen. That AT doesn't influence the next state. Okay, so AT may not influence, let's say, xt plus 1. Okay, that doesn't happen in contextual bandit. But what does happen in contextual bandits is this: that AT does depend on history. Okay, in that sense, there is dependency. But in RL, it's not just that AT depends on history, but AT also influences the next states that we'll see. Okay, so it's like even more dependency than you would expect in data. So that's why the data, the optimization problems are definitely different. The way you figure out the policy is definitely going to be different. Okay, because it has to address this issue, right? The data is dependent on what you did, what you do, and what you do depends on previous data. Okay. Yeah. Is that clear? I mean, so in this picture, I'm just trying to show you that there's also.
Yes, yeah. Professor.
Okay, another quick point, I think maybe something that may or may not confuse you is that even supervised learning, let's say that your action, your next, your class label, of course, depends on the training data, like because the training data led to your function, and therefore your training data influences what class you'll predict, right? That dependency is there. I mean, okay, but it's a little bit more subtle here when I say AT depends on history. Right, so the action, the AT depends on history because you can only take, okay, I think I should add AT depends on history and what is it called? Let me actually use the right word here. And we have bandit feedback. Which means that, let's say we are in some state, okay, some xi, for which we took an action AI, right? And we got some reward Ri, right? We don't know what would have happened if we took some other action for the same context. Okay? Whereas in supervised learning, you predict a class. Let's say you have an image of a cat and you predict a class dog. Of course, you get a 0 reward. I mean, it's a incorrect answer. But you also know what the right class is. If you had chosen cat as a label, then you would have gotten the +1 reward. Okay. So there is bandit feedback, which is the issue. Okay, that's what causes the data, dependency aspect. I mean, there's bandit feedback and dependency together, make it different from supervised learning. In supervised learning, what they call it, okay, the equivalent term here is called full information. Just means that you have a classifier. If you incorrectly say the classifier, the answer is, when you're incorrect and when you're correct. Okay. Whereas with bandit or contextual bandit setting or reinforcement learning setting, in a given state, you can take an action and you get a reward, but you don't know what is the best action to take. Okay, there's a difference. It's not like you can change the action to say, hey, instead of taking action 1, you would have taken action 2 because you would have gotten a higher reward. You wouldn't know that unless you do that. Okay. Whereas in classifier, if I say class 1, it could be wrong. If I say class 2 instead, I could be right. You would know that. Okay. I hope I didn't confuse you. What I'm saying is these are the two aspects for contextual bandits, and then actions influencing future states, and actions influencing future rewards or t+1 and so on, are further differentiating characteristics. Okay, but the similarity is that at the end of the day, you want a mapping. a function which maps from a state to an action. In that sense, they are similar, because in supervised learning, you want a function which maps from states to a label. Okay, and since you want a function, there's going to be a typical optimization problem. Remember, we always said, we were doing gradient descent based techniques with many of the models that we saw previously. Similarly here, when we eventually get to DQN, we're going to use a similar gradient descent based technique and appropriate loss function, and they're not going to be very different from supervised learning objective. Okay, but there are differences and there are some similarities. That's what I want to get. That's what I want to say here. And I'm really running out of time, but let me at least mention a couple of more basic aspects of an RL, I guess, to describe the RL problem and the and any RL solution. Okay, so any RL solution, which means that any an RL agent, an RL solution is just an RL agent, will typically include one of these three objects. Okay, one or more of these three objects. Which is a policy, which we just saw, that F function, which goes from a state to an action, is a policy. Okay, we already know what a policy is. And there's going to be two more objects. Okay, one is a value function, the second one is a value function, and the third one is a model. Okay? Value function is the new, I guess, a new idea, and that's actually underlies the algorithm that you look at assignment for question 3, which is DQN algorithm, as well as something called Q learning algorithm. We're going to look at value function at length, maybe not, if not this session, next session. It's basically a measure of how good each state and our action is. Okay, so it's a function which says, hey, if you're in this state and you took this action, this is a great combo. Okay, this is a great pair. Or it could also be a function which says, hey, you're in this state, this is a great thing to be. So it's a score that you can think of a score being ascribed to each state, or it's a score being ascribed to each state and action pair. Okay, that's what it is. Higher the score, the better state action pair it is, or the better state it is. Okay, that's roughly the idea, and we'll formalize it later. And a model is just an agent's representation of what the environment is. Okay, so remember, environment is supposed to give me a next state, st plus 1, if it sees an action at. Okay, given an at, it will say, hey, you took an action at state st. I'll tell you what the next situation is, which is st plus 1, and I'll also give you rt plus 1. Okay, so how do we go from this couple of things to these couple of things? Okay, so environment will do it. In real world, if you take an action, if you really have a car and take a left turn or right turn, you will actually see what will transpire. Okay, but a model is just a model of what would happen if you take action at in a state st. Okay, it's just I guess an approximation of reality, right? So and that can be encoded using some function. In fact, the function we already saw, for example, we have a function which is p of st plus 1 given st, the Markov assumption. So this is a distribution. So a model is nothing but something like conditional probability distribution, which says, hey, when st given in state st, you took an action at, and you get to state st plus 1. Okay, it's a conditional probability distribution. That's all. Okay. And we'll see more about all these three objects more and more in the next session. But let me get started with at least a couple of these objects. First is a policy, as I said, is this a function? Oh my God. Okay, it's a function which goes from a state to an action. So I'm going to represent any generic state with little s and any generic action with little a. Okay, and you can also have policies which are deterministic, which means that given a state, it'll exactly say this is the action. It's like an argmax over your distribution of actions. But if you had a distribution of actions, which is typically what you'll see, like if any classifier, it's not producing a single class, right? It's producing a distribution of classes, and then you're taking an argmax. So in general, you can say, hey, a policy is a distribution of actions. So it's basically saying, given a state, here is a distribution of actions. Okay, it's a conditional probability function. Yeah, for example, a policy here. So let's say this is a maze, and here the policy, for example, could be, hey, go straight, go up, down, maybe like this. This is one policy. This is clearly the policy which lets you go from start to end. But you can have other policies, right? You can say, hey, go like this and go south, and then again come back up, and then go right. Okay, so there are many policies. we don't care about rewards at the moment. Actions are north, east, south, west, let's say. And state is going to be agent's location. Okay, so state is agent's location. Rewards are, let's say, -1 per time step. So every move you make, you get a -1 reward. So it's intuitive because if you finish the maze quickly, then you get the least number of -1 accumulated by you, right? So if you don't finish the maze too quickly, then you'll accumulate a lot more -1s. Okay? And here is the exact, is an example of a policy that we just, I just drew something, but you can also, I mean, this is also a policy that every state is just saying, hey, go left. In this state, it's saying go to east. In this state, it's saying go to west, and so on. So that's exactly what a policy is. It's just represented here in a diagram because clearly the states are these white blocks in this maze. So that's why it's easy to say what the policy is. But in general, what a policy is, a policy can be different. Okay, for example, a different policy could be, hey, go north here, although you cannot go north there because of the black wall there. But there could be many policies. Here is an example of a policy. Okay. Yeah, let me define just what is the definition of a value function and then stop here. So value function is, as I said, it's the score that you want to assign to a state or a state action pair. So let's stick with state for now. So a value function is a function which given a state will say, hey, here's a high score for you, high 10 units. Okay, for some other state, it'll say -10 units. Okay, it's just a score for how good a state it is for you. Okay, for the agent to be in. So it's a prediction of the future reward from that state. So how do you score a state? If you're in a state from which, if you take a bunch of actions, let's say arbitrary actions or some specific action, you get lots and lots of rewards in the future. That means that being in the state is good. Okay? Maybe you're in some other state. Let's say the car, self-driving car is the edge of the cliff, and you want to go forward. Being in that state is bad because if you take the forward action, you're gonna, literally not have any more rewards to collect. So that's a bad state. Okay, so it's basically just a way to evaluate being in good states and being in bad states, and this is an intermediate object that is useful for later on to define algorithms. Okay? So formally, a value function for a state is just the expected future rewards that you can collect starting from that state. Okay? Starting from that state at C being little less, hey, how much reward can I collect? Let's say we fix a policy as well. Let's say the policy is whatever policy. Remember, it's a function. From every state, it'll say what action to take. Given the policy from the state, hey, here's the reward I can get. Here's the other reward I can get. Here's the other reward I can get. Let's add them up and take an average. So that's that number is some scalar number, like a fixed number. It's not a random variable, right? So that number is the value of the state according to policy pi. And we'll see an example. We'll continue from this slide onwards next session. I want to stop here and see if there are any last minute questions. So what we've done so far? Yeah.
I had a question just kind of generally. So I guess, can you go up to 2 slides? Yeah. All right. So what the reinforcement learning, we didn't really talk about like costs associated with actions. So like, I think in the most simple model, all the actions are equally costly. But let's say you want to design a model that, like, for this example, let's say you just don't like going east for whatever reason. You can imagine, oh, there's wind blowing in the east direction, so it's harder to walk that direction. You might want to model that. And so I guess I was sort of just wondering generally, like, I imagine the simplest way to model it is you just say, oh, this action has an associated cost. And you just put that into the value function. Yeah. But there's also seems
not putting in a value function, but yeah, you can define that cost. Value functions are something that depend on your policy as well. Okay. So value functions are something that you derive given the specification of your problem. So the costs are part of the specification of the problem. Okay. So if you wanna specify that, as I said, east is bad or west is bad, then you specify the problem appropriately by defining the rewards.
Yeah. Okay. Yeah, but yeah, I was saying, okay, the simplest way to minimize actions or to try and reduce on bad actions is you just associate a cost with a specific action.
Yes.
But that seems like a pretty blunt way of doing it. And it seems like you can have much more sophisticated ways of doing that. Like you could say, okay, let me look at my past history. And, if I, go east more than 5 times in a row, or if I do the actions that lead me to the same state over and over again, like, getting caught in a loop, that you can associate cost with, that type of thing.
You don't have to. Yeah, I agree. I mean, but that comes down. I think maybe you're thinking about how to design a good agent, as in like how can agent learn by itself. So we are not at that stage yet. We are just specifying the environment. Okay. So all this, what you're saying of how environment gives feedback to the agent, is all specified inside the environment. Okay. So the environment.
So you associate it with the environment, not with the agent.
So. No, so the specification of the environment is for any given, so environment, let's say if it's a Python function, it says, hey, tell me tell me what action you took. Okay. The environment also says, takes these two as inputs and says st plus 1 and rt plus 1 as the outputs, right?
Yep.
So as long as you can define this function, we will look at we'll look at one algorithm, actually, not many, but we'll figure out how to take good decisions. Okay. And in fact, those decisions will exactly avoid the types of things that you're saying. Like if 5 times in a row, if I take a bad action, if I take a certain action and I know that I'll get really bad rewards, then I'll not take it. Okay, so that's the responsibility of the learning algorithm, to learn a good policy. Okay, learn a good policy, or actually F or pi, which goes from action AT to which goes from a state to an action. To an action AT. So we will figure out how to learn good pies, but specifying the environment is what we're doing.
So I guess I was thinking in my mind, you can tie the cost to the environment. So you could just have a rule in the environment that you say, oh, if you travel east, if the action is equal to east, return a cost of, whatever the cost would be plus 5, or,
Yes.
And I think, I could see how you could put basically any rule you want. You could associate it with the environment. I understand that.
Yes.
I guess I was just thinking from a training complexity point of view. You may also want to put some of those rules on the agent side rather than the environment side.
No, the agent's only API is, it tries to take an action, environment says, hey, the immediate reward for this is bad or good or something. So agents, the only way the agent improves is through this incremental feedback that it's getting, rewards or costs, whatever you want to call it. Okay. Costs are just opposites of rewards. So agent, only by looking at rewards over time, figures out what's the best thing to do. Okay, that's the only API. Of course, you can say, hey, agent knows a little bit more about the environment, and so I want to build in some extra prior knowledge of, hey, agent, you should not take action or east or something. But yeah, you can certainly do that.
Yeah, I guess I was thinking that would be potentially useful, because I was sort of viewing the agent as like the equivalent of like, comparing it to supervised learning. I was thinking, okay, if the agent has no prior knowledge or anything like that, that's sort of the equivalent to having a bunch of fully connected layers in a row. And while, you could theoretically do everything with all fully connected layers, often you want to do like convolutional layers or whatever, your softmax or whatever to get convergence more quickly. And I was thinking in the same way, you might want to build inbuilt stuff rather than putting it, like, even though you could theoretically tie everything to the environment and the costs, you may want to tie things to the agent side to simplify model complexity.
No, what you said is exactly correct, that if we can certainly restrict the agent and add constraints, priors, regularization on the agent side, or even like instead of using linear layers, you can use con layers depending on the input and all that, or many other types of constraints you can put on the agent side. Environment, sometimes you get to design an environment, sometimes it has to just reflect reality, or sometimes you are actually navigating the reality, you don't get to control it sometimes. Okay. But agents algorithm, you certainly can control a lot, and depending on your domain knowledge, you can always incorporate prior knowledge there.
Okay. That's thank you. That's useful.
So far, by the way, just to summarize, just to wrap up now, we have not looked at any algorithm yet. Okay, we're just defining different components in the RL problem. we'll look at an algorithm towards the second half of the next session. Okay, so thank you everyone. Apologies for going over time. And if folks have still questions, then please stay back and ask. I'll stop the recording now.